Hello, we are going to talk about how two waves or many waves are interacting one another to result in a very interesting phenomena, and we call it superposition of waves. So let's try to understand how the waves are interacting each other. So superposition of waves is the common conceptual basis for interference and diffraction as well as polarization optics. The question is, what happens when two or more waves overlap in some region of space? So that's the uh, very important questions we are going to discuss. So we start with the wave equation here. And linear, this with differential equation is linear, so that any linear combination of its solutions where psi I is the solution of the wave equation, and if you have a linear summations, then it is also solution of wave equation. Okay, so that's the linearity. So if you have two waves summed over, and then it is also wave that satisfies the wave equation. So now let's try to think about superposition of two waves. First, start with the same frequency, and the two waves meet each other at point P traveled by the x1 and x2 for wave 1 and wave 2. And then phase term is given by omega t minus kx1 plus epsilon 1, omega t minus kx2 plus epsilon 2. So remember that it has the same frequency such that omega and omega are the same. And then we have alpha 1 and alpha 2 is given by this one. And then if we add them together, epsilon, E1 and plus E2, and then by sign relationship, we get E0 sine omega t plus alpha here. And then E0 is given by this relationship, and alpha is given by this relationship. And the resulting wave is also oscillating with a frequency, but it has a different amplitude and different phase term. Okay, the phase difference here, alpha 2 minus alpha 1, has a two terms. One is initial phase difference, and the other one is so-called optical path difference, OPD. And then if you look at here, k 2 pi over lambda is k, the wave number, x1 minus x2, and then this is given by k0 times lambda, capital lambda is given by n times x1 minus x2, the spatial difference times refractive index of the medium is OPD. Okay. So here's some cases. The blue and green lights are summed over, and the red is the outcome. If you have a same amplitude for blue and green, and you get amplitude is going to be doubled. Okay, and if the blue and green has out of phase or pi phase shift, then we have a red which is a 0. Okay, and it is summed over and then to result in cancellation of waves. Okay. So for the same frequency, we have various cases depending upon initial phase and the optical path difference. And then now let's try to think about two waves with the path difference. here the same, once again, same frequency, but the phase difference given by delta x. Okay, and then resulting wave is given by amplitude term and this phase term. Okay, amplitude here is the function of a phase difference delta x, and depending upon delta x, your amplitude will oscillate by cosine k delta x over 2. Okay. So if delta x is much smaller than lambda, or delta x over lambda is given by plus minus 2m, or m is its integer, then you get 2e naught. Okay. So initially it's given by E01, E02. Let's assume that E01 and E02 is E0, and then you get double. Okay, but in the case delta x is given by half integer, then cosine half integer is 0, such that you get amplitude is now 0. Okay. So here's the exercise. You want to try that. The phasor is just a general way of representing the complex number, the phase. Okay. The amplitude is 0, and the angle is given by this one, the phase. And now let's try to think about this same frequency, but with not only 2, not only 3, but with many numbers, I equal to 1 to n. Okay. Each of wavelengths, each of a wave has amplitude, and each of wave have this phase term. Okay. And then total electric field is going to be given by this one. So that amplitude is given by these equations, and the total phase is given by these equations. So for the coherent cases, that means the phase are related. In specific case, let's assume that they are the same. Alpha I, alpha j the same. Then if you look at this, then this term goes away, and then you get here E0I plus 2 E0I over E0j, and this is nothing but n times E0I squared. But in the case of a coherent sources, random phase, and the second term is 0, and then here only this term survives. So that what we have here is that in the case of a coherent amplitude is going to be n times E naught I squared. Okay. But in the case of incoherent, we get these expressions. So depending upon the coherency or the phase relationship, you will have a very different result. And now it's time to think about different frequencies. Thus far we have considered the same frequency, but now we have omega 1 and omega 2, and the corresponding wave number is k1 and k2. Let's assume that k1 is larger than k2 and omega 1 is larger than omega 2. And then as a result of the two-wave interaction, we just summed over, and then we get this relationship, and the result is shown here. And then we have two different waves with a different wave vector, k1 plus k2, k1 minus k2, and different frequency, omega 1 plus omega 2 and omega 1 minus omega 2. So we just have k bar and omega bar, km and omega m. And the average angular frequency omega m is given by this one, Km is given by this one. I'm sorry, this is omega m is this one, Km is this one, omega bar is this one, omega k bar is this one. So what is happening here is that we have a time-varying amplitude and we have this harmonic term. So if omega 1 is omega 2 very equal to very similar, then omega bar is much larger than omega m. Okay, and we will have a very slow varying amplitude. Omega m is very slow, very tiny, so that as a function of time it is slow varying. And then this omega bar is much larger, such that it is rapidly oscillating down. And then in the case of irradiance is well proportional to electric field square term. And then this is given by this one. And then we have interestingly, we have this beating frequency, omega 1 minus omega 2. Okay. So that two waves with a different amplitude produce beats with that is the important one. Okay. Two waves with a different amplitude and different frequency will have beating. Here's the case. So we have a outcome is here two waves. There's two waves, and then as a result is the red one, and this azure sky color cases. So this is the red is the electric field, and this cyan color is the irradiance. This. And then we have, for these cases, we have a phase velocity and the group velocity is different. Phase velocity is given omega bar over k bar, and the group velocity is actually d omega bar over dk at omega equal to omega bar, or omega m over km. That means velocity of a modulation envelope. So that this envelope is traveling, okay, and inside the envelope there's a high frequency term. Okay. So as you might know, we have considered the addition of waves or superposition of the waves, and by superposition of the two waves with the same frequency or different frequency, we have learned that especially this case, superposition with slightly different frequencies, and then the result is the beating, the red, and then the irradiance goes like this. Okay. So we note that there is an envelope, and inside there is a high frequency term, and total envelope will also propagate. That's the information. And for the envelope, we have a group velocity, and for the phase, we have this phase velocity. Okay, thank you.